I mentioned trust, right? And I mentioned that there are two reasons, two proofs of trust. And first one is the voice of customer. And we heard this voice. And the second one, what do you think? What is the second kind of really solid proof of trust? Actually, it's the dog fooding. And we are making our dog fooding. So we create infrastructure, and we have our own internal team who build different models and make a lot of experiments and so on. So please welcome Karina, who will deliver a really interesting story about the cases they work with.
Hello, everyone. My name is Karina Zainullina, and I'm a ML engineer in our in-house Nebius AI R&D team. Our goal, our team works on applied research, which is closely aligned with Nebius's core business, providing computational infrastructure to AI builders. And today, I want to tell you an exciting new research we've recently begun exploring, building agentic systems that become increasingly intelligent as they leverage more computational power. So yeah, most probably you noticed that LLMs are getting better and better every day. New benchmarks emerge and quickly get saturated. And in many domains, currently, LLM-based systems work even better than the average human. And the progress continues. The most recent introductions in the capabilities of LLM-based systems is, of course, reasoning. We spoke about it before. We heard about it from the Synth Labs. So I'll tell you about the reasoning as well. So what is reasoning? Reasoning is the ability of the model to kind of think, utilizing compute and generated tokens. And when model generates better answer based on these tokens and based on this compute, the more compute it takes, the better the answer is. And the reasoning was first introduced by OpenAI with the O1 and O3 model. And recently, they were followed by other big AI companies, such as Google, Anthropic. And of course, let's not forget about DeepSeek, we already mentioned before, who also released the guidelines on how they built their reasoning ability. And that also benefited open source community. So the key enabler behind reasoning is reinforcement learning. Reinforcement learning is a technique to train the model when we don't really have SFT data, and we allow the model to try different things, and then just score and provide the model feedback on the things it tried. So we kind of punch model for bad actions and reward it for good ones. And reinforcement learning is now quite powerful mechanism, which works almost everywhere and allows us to introduce capabilities the LLMs didn't have before. But reasoning, in terms of mathematical reasoning mostly, is a constrained case of reinforcement learning. Why? Because the thinking process, and during the thinking process, we don't provide any feedback to the model. We provide the feedback only for the output. And the thinking process itself isn't somehow rewarded or punished. It just happens. And for those of you who are familiar with RL, the reasoning environment is fully observable environment that doesn't give any feedback in the middle. But what we really want, we eventually want to get a system that works, like a LLM-based system, that works, makes some actions, receives feedback for these actions, and this process continues until the system reaches its goal. For example, you can imagine navigating website, searching some information, the agent does it, or coding, the agent adds some code, then tests it, and so on, until it reaches the solution. So let's speak about the later case. It's called agentic software engineering. We want not to get like code assistant, but to have a fully autonomous system. We provide the repository and task description to this agent and to this system. And when it adds some code, generates tests, and so on, until it produces patch, the solution to the problem. If done well, this area has a huge potential to impact, because we can significantly increase the speed of software development process, which is really good. And despite being quite new, it already has well-established benchmarks. One of them is SWE Bench, created by the group in Princeton, and we'll speak about this one later. And now, currently, many systems already work well in this benchmark, but, well, not perfect, allowing some room to improvement and to do it better. And also, it allows to enable future progress, because if there is something that works well, we can collect data or do something similar to this system and do reinforcement learning on top. And I also want to mention that the best current systems work based on proprietary models. But open-weight models catching up quickly, allowing further progress outside frontier labs. Also, as the best systems work with proprietary models, they are mostly based on prompting or handmade scaffolding. There is no our way to build such systems. However, this is really unreliable and violates something called the bitter lesson, the historical observation that even though in short term we can build over-engineered solution, in long term the solution which scales well with compute or uses large-scale search and data-driven learning often will win out. So the question arises, how to build such a solution? I already mentioned that currently many systems are unreliable. What do I mean by that one? Here you can see something called SWE agent scaffolding made by the same team who created SWE Bench. And you can see the average performance on 50 subtasks from SWE Bench. Performance is just the number of solved tasks in percent. And the best of n performance, when the task is considered solved, if it was solved at least once in n runs. And you can see for n equal 5 that there is almost two-fold gap between the average and best of n performance, meaning that sometimes tasks are just solved occasionally, but not reliably. And the plot on the right for you, or on the left, the success rate per program further illustrates it. Yeah? So here we print success rate per problem out of 5 runs. And you can see that there are a few runs, a few problems which were solved like with 100% reliability and a long tail of problems which were solved just occasionally, once in 5 runs. So, can we fix this unreliability? And why does it happen? When we run agent, we run it from start to an end in a single pass. And we wait for agent to make all the good decisions or to perfectly fix its own mistakes. But it's not always the case, because both events are stochastic. We work with LLMs, yeah? Everything is stochastic. And even if everything was good, but one mistake was made, I don't know, in the middle of solution trajectory, when whole solution could become wrong. That's bad. So probably we need to deal with it. And there are a few ways to do it. From the bitter lesson, we know we can do either training or guided search. But with training, there is a problem. We can't fine-tune proprietary model. We don't have access to it. And if there is no API for fine-tuning, then there is no training available. It's bad. The second thing we can do is guided search. So instead of just running agent from start to an end, we want to check multiple possible solution trajectories. Like we can do MCTS and some searching techniques. However, mostly there are like exponentially many solution trajectories because from each state we can try K actions and so on and so on. So impossible to check them all. What can we do here? So we can use some sense of intuition. I'll speak about that one later. In order just to, which can guide us to the subtree, which will most probably solve our problem. So we want to go to the potentially the best subtree from the tree and only explore this one. And later we just commit to the one result we think works the best, and that's the answer to our problem. These guided search approaches showed good performance before in things like mathematical reasoning, so probably we can use them here as well. But we have an issue, because it's not going to be easy. Yeah? The thing is that there is one issue called the non-serializability. Many powerful guided search methods like MCTS or something, tree-based mostly, work as follows. So we have one state, and we try multiple actions from this state. And we check what's going to happen if we apply different actions. And in order to do so we need state, 0, and actions we want to try. But what if we apply A1 action, for example, to a 0, it's going to change the state irreversibly. So there is no scenario to get back to a 0, and we can't just easily roll back. When the only thing we can do is to copy a 0 multiple times and apply each action to its own copy. Easy, but the thing is that what if there is no copying mechanism in our system? We can't just duplicate the state. That's sometimes happens, and it happens for a Docker container, where these software engineering agents run. And we need to deal somehow with it. Probably we can't use such types of search. But there are a few types of search we can still do. And we're easy, but yet very powerful. And I'll speak about them. So one of them is one-step look-ahead, and the second one is parallel search. Let's speak about one-step look-ahead first. So we have state in the middle of our solution trajectory, and we generate actions based on this state. And we want to choose one action from this state. We will continue with this action afterwards, and so on and so on. Yeah? And we'll get to a better result, like this. So in order to do so, we estimate before committing to the action, before really doing it, we estimate each action, and then choose the action with the highest score. Yeah? And our score is this sense of intuition, whether this action will help us to solve a task or not, whether it will lead to the solution or it won't. This happens in a stepwise manner, so we do it every step, same mechanism. And the second type of search, on the other hand, is parallel search. Instead of just doing like a stepwise check and stepwise scoring and choose, we run multiple agents in parallel, just from the same initial state. So we have state as 0, and we run, for example, 5 engines from the same initial state. Nothing else similar, just run them in parallel. For this one, we need to copy the initial state, of course. But initial state is mostly the task description, easy to copy. And afterwards, we also do scoring and choose a trajectory that works the best for us. OK, so do these types of search really work? Here's something. Here are the results for look ahead. And we apply it on top of the Qwen-based in-house model we trained and GPT-4o model. And we use 4 candidates here. So we choose from 4 actions. And as you can see, it works. It significantly increases the success rate for both Qwen-based and GPT-4o-based models. And also, you can see the success rate per problem. And here also, we not only increased the reliability of tasks we were already solving before, but also added new ones. Cool. Also, I want to say that everywhere we use Swift agent scaffolding, as we did before. And in order to estimate actions here and on the next slide, we will use the Qwen-based model. And here's the next slide showing similar improvements for parallel search with number of parallel runs equal 5. And as you can see on the previous slide and here, we use the Qwen-based model for estimator. This means that the weaker model, the Qwen-based one, it's smaller, like 72 billion parameters, can guide the bigger model, the GPT-4o. And it's really good property to have. So we don't need the stronger guiding model. It is really important. What's good about both of these types of search is that we don't really, they're independent of each other. So we can combine them. And this allows us to have twofold improvement in performance for both GPT-4o and Qwen-based model. Perfect. Both of these methods also scale with compute. Here you can see the dependency between success rate and the number of candidates in look ahead. The more candidates you have to choose from, the better the success rate is, almost. And it means that you can invest more compute to get better results, giving you a way to trade off cost for higher quality. And the same works for the parallel search. The more parallel runs you have, the better the performance is. And also here we have the best of n, same as we saw before. But it's like potentially unobtainable upper bound for the parallel search. Because it means that instead of the model estimator, we use something called Oracle. It is an idea that our estimator knows the ground truth. It doesn't work, yeah? We don't know ground truth before we solve the task. So I showed you the results of search, and I also want to mention where does this intuition come from. What we do is we train a model. Everybody does, so we do as well. It's kind of verifier in mathematical reasoning. So we train model to predict the probability of each action to lead to a successful result. And how we train it? We get solution trajectories. This is basically the concatenation of observations and actions. And we predict whether this trajectory will be successful or not for each action. Speaking in technical terms, if you are familiar with reinforcement learning, we actually train action value estimation. function. We train action value function, like we try to estimate it. But still, we have some problems. One of them is that the trajectories can be very long. This means that activations for these trajectories take a lot of memory and really big. For this, like the Nebius platform is of a great help, and we have H200, which allows us to have more memory. And also, we do a lot of context parallel training. We not only train on one host, but on few hosts and so on. And we really need fast interconnection. But luckily, our infrastructure allows us to easily do all this training. So, I already showed you that with 20 times more compute, we can achieve a twofold performance in a twofold improvement in success rate. And even these simple search methods work really well and also increase the reliability of the agent. But 20 times more compute doesn't really mean 20 times slower because both of these methods are parallelizable. Of course, the latency is affected, but really a little bit. So the latency is almost unaffected. And also, it is important to understand that the next twofold improvement will require a lot more compute because the dependency between the compute and the quality is nonlinear. So probably we need to find more sophisticated methods that would be more compute efficient. However, we still have non-serializability issue, and we need to deal with it. And we need our infrastructure to be prepared for such methods. And also, another interesting question for us, whether we can distill the search back to the original model. So if we can somehow, with some techniques, distill it back, it means that when we can use this model as the original one and do a search on top of this model, again improving the performance. And it will lead, hopefully, to the continuous self-improving cycle where, I don't know, we'll get better and better success rate. Thank you. That's it from my side.
Nice story, right? So, questions? Any questions from you guys? It seems you are tired today, right? Any? Yeah, here, the gentleman on my right.
So you explained how it's 20x more compute. And is that for the stacking of both parallel and the next step search? Because I can imagine if you combine both, then you're actually having a lot of copies, like at least to combine them, yeah.
Yep, sure. So,
yeah,
I tried
so
to.
Okay, I thought it was a mistake, and that's why I took your.
Yeah,
Sorry,
I
my
didn't
bad.
on purpose. So yeah, in terms of compute, we don't lose compute on coping state because it's just coping, yeah, process. So where does the compute go to? The first thing, actually it goes for one step look ahead to generate multiple candidates, because instead of one candidate, you need k candidates. And in one step look ahead, for each state, we do 4 candidates, meaning 4 times more compute, just for generation, you know? We generate more. We generate 4 times more candidates. And in parallel search, we just run agents in parallel. This means that each agent has its own compute. So 5 times more compute. And combining them together, 4 multiplied by 5, we'll get 20.
Okay, and won't you do one step look ahead for every parallel search? Won't it be for par 5 if you do that?
So yeah, we do it for every parallel search. So you can imagine inside each parallel search, we have one step look ahead, you know? So each run of parallel search inside it, yeah, we have 5 runs. Inside each of runs, there is one step look ahead. You can do just parallel search or just one step look ahead, but combining them together works the best.
Okay, and one more question.
Sure.
So you mentioned you're training a model which essentially is acting like a verifier to give you the intuition for every single step.
Yeah, kind of.
So there will be some bias towards that trained model, and you're kind of relying on how good that trained model is for your search eventually. And you also mentioned you have an Oracle verifier which is helping train the model, I think?
So we have Oracle verifier when we already know the results, yeah? So for training data, we use Oracle verifier because at the end we can just check, yeah, different trajectories and understand whether it works or not. But during the inference or during the development process, the agent doesn't really have this, so yeah, that's the thing.
The first question about the bias towards your trained intuition, isn't that a problem eventually?
So it depends on the bias you're speaking about. We can probably speak about it later, yeah, deeper.
Just wait a second, please take a microphone.
I think my question is more on integration between hardware and software for test time compute and just moving forward. If you step back to look at what I mean by hardware mixed with software is if we use the ratio of performance, you mentioned for the software side, 2x is going to be much harder as a step function to get to, okay?
Yeah.
So now on the other side of the fence, on the hardware, you have also performance ratios for H2s to Blackwells, for example. So there's efficiencies happening on both sides of the field. When you try to put these together, what does the ratio look like right now between the two halves when you put them together of is there a big gap that's going to start happening soon, whereas NVIDIA machines being too generalist cannot solve for the amount of success rate we need when we go above 2x? And to further the question, do you see a short to midterm run in the future where Gen AI ASICs are going to be kind of taking over a lot of this specific RL test time compute workloads just to solve inference ASICs?
Let's start with the first question. So regarding the compute itself, yeah, we use either H100 or H200. But the thing with H200 is that in terms of teraflops, if I'm not mistaken, they're same as H100. So they're just bigger in memory, yeah. So yeah, it doesn't change this ratio because they're just bigger in memory, but we are speaking about the teraflops here. And regarding the second question, can you repeat it? I didn't quite get the idea.
Well, the first question was the first question was actually a difference between the H series or H1, H2 versus Blackwell, and how big the performance jump is compared to the 2x success rate that you're saying is very difficult to achieve. That's the first question.
So we only use H100 or H200, and I'm not sure we were
Got it.
so we haven't tried the next versions yet. But I think so the compute here goes mostly from that we need to do some runs in parallel. So even though each run itself will be faster, we'll still struggle with this thing that we need, just more runs or to generate more action candidates. So I think the ratio itself won't be influenced by the computational power of the GPUs. It only will be we'll only see how fast we can do one full run, but not the search itself.
So effectively, more runs, to have faster processing for more runs is more flops.
Yeah.
Okay. And then the second question was, do you believe there's going to be a surge for a lot of Gen AI ASICs? There's a lot of ASIC startups in Silicon Valley right now.
Okay.
That I think they're trying to solve a lot of this test time compute issues.
I think the issue goes from the inference. Yeah, we're speaking about inference here mostly. So it actually depends. Probably yes, but I'm not sure. It would be interesting to understand it fully.
Okay, let's go with the last one. Who was the first? So, the gentleman there was shaking his hand for a while. Yeah. Sorry, guys, it would be the last one, but please reach Karina.
Thank you.
Yeah.
A couple of questions that for influencing. If you do parallel, is that context size limited? One. Second thing is, if you do cosine symmetry, if you don't do sequentially, that if your context and content getting bigger as I'm increasing, your parallel will not increase in the resolution, because if context decrease, your probability error will actually be more distorted in that case. So parallel will not recover the accuracy. It will give you the branching prediction better by search faster, but that's about it.
Regarding the context itself, so in parallel search, all the runs are independent of each other. This means that the context only depends on the model's ability. Yeah? Currently, models have, I think, 128,000 tokens, like 131,000 tokens. Yeah, and sometimes, most of the times, here it's more than enough, because the tasks are not so big, and if the models goes the right way towards the solution, it will eventually get to that one in this number of tokens. And regarding the second question, I didn't quite get it, so probably cosine symmetry.
Yeah, if your language model based on cosine symmetry for probability for branching things. If your language model is based on cosine symmetry or probability, you do trace one by one. If you do parallel search, the problem is each one predict to the layer will be slightly different based on previous apart. And that became challenging to monitor and figure out which one is accurate. Because the longer you do parallel search, the depth of probability error you get higher, because if your context cut in half, let's say you have a long sentence, your probability error will go double. Well, that's 25% minimum. It's not something you can recover easily from parallel search, because you basically just do branch predictions at that point.
So regarding, I think it's not the case, the context window itself is not the case for parallel search. We can speak about one step look ahead more in this case, because we want to do to generate multiple actions from the same initial state. From the same state, yeah? So in parallel search, all the runs are independent, and context window is independent for each run itself, yeah? So we don't want to to have, I don't know, one action dependent on each other. For one step look ahead, on the other hand, it's not the requirement, but it would be good that if action is unique, yeah? And we can generate actions in a way you suggest, just to make each action unique. Yeah, and it could be the problem. Now we just generate actions without thinking about the unique actions, but it's a good idea. Thank you.
Okay, guys, thank you very much. And I saw that there were some other questions, and Karina is a very bright person. It's very easy to find her after the session, please, and speak it loud. So.